In this supplemental video, we're going to quickly cover how to sketch polar curves using two different methods. So the example we'll actually cover will be trying to sketch this polar curve. R is equal to 1 plus 2 cosine of theta. And there's two different methods, like I said, that we can approach sketching polar curves. The first method we're going to use is basically making a table of values or coordinates r comma theta, and then plotting those points one at a time. So let's actually dive into that really fast. So I'm going to do a lot of the legwork here. So if we make a table of points, we're really choosing a bunch of different theta values. And then for each of those theta values, we'll be finding their corresponding polar radius. So we'll just take that theta value and plug it into our polar curve for theta to find the corresponding r value. So and I've chosen this is between 0 and 2 pi for theta, and I've kind of just evenly spaced those points out in kind of steps of pi over 4s. And we can go ahead and see, and well, do we need more steps? Do we need less angles than that? And kind of play around. And some of the other things you might see is, as we've evaluated those angles or those polar curves, 1 plus 2 cosine theta, and many different angles. Some of the things we see showing up are sort of like these factors of square root of 2, where square root of 2, if you're unfamiliar, is just about 1.4, and a lot of change after that. So let's go ahead and try to sketch some of these curves or some of these points right away. And remember, for us, polar curves live on the XY plane. So this is where we go ahead and sketch them, on the XY plane. Some of the things we can look at is just over our R values that we have, what is the furthest it looks like we're ever going to be from the origin? In this case, it really looks like we're going to be about 3 units away from sort of what happens at 0 and from what happens at 2 pi. Those seem to be the largest R values we have. So let's kind of try and set up this XY plane according to those dimensions. All right, so let's go ahead and start plotting some of these points. So the first point is when we're at an angle of 0, which is just along the x-axis, and we move out a distance of 3. So along that x-axis, we would move out a distance of 3, and that would be our first point. So it looks like we have 1 point down, and the next point I'm going to plot is not at pi over 4 for theta. I'm actually going to skip that one for right now and plot at pi over 2. Just because now if we're at an angle of pi over 2, remember, we're basically straight up along the y-axis because we're defining our angle thetas off of the x-axis for that matter. And we are at a distance of 1 away. So even though we're along that positive x or positive y-axis, we're 1 unit from the origin. All right, let's keep going. I'm going to skip over 3 pi over 4 in the same way, and next look at what happens at pi. Well, in this case, normally we'd be along the negative x-axis at an angle of pi. Again, because we're defining our angle from the positive x-axis. But this time we see something special happen in which we have a negative r value. So because we have a negative r value, rather than move out one direction towards that negative x-axis or in the pi direction, we actually reflect over the origin and we land in the positive x-axis side. And again, that's because we have an r value of -1. So, okay, so let's keep moseying on along here. Our next value we'll try is 3 pi over 4. Again, an angle of 3 pi over 4 would just be straight downwards along the negative y value, and it looks like we are a distance of 1 away from the origin there. And finally, we'll end with this angle of 2 pi, which again is going all the way around our axes, and it looks like we're again on the positive x-axis. And we move out a distance in this time of 3. So it looks like we're actually ending at that same point we started at. All right, so that covered all of those kind of angles, 0, pi over 2, pi, 3 pi over 2, and 2 pi. Let's go back and fill in some of those other angles between. So if we're at this angle of, say, 1 plus square root of 2, or sorry, this angle of pi over 4 at r equals 1 plus square root of 2, an angle of pi over 4 would be basically cutting through that first quadrant evenly. And we go out an angle or a distance of 1 plus square root of 2, so about 2.5, if you will. So just roughly what 2.5 looks like is maybe somewhere around there. So I'm going to first start connecting the points. We're connecting 0 to pi over 4. So remember, at 0, we started there. Pi over 4, it looks like we're going there. And since this is just a really crude sketch using individual points, I'm just going to draw straight lines for the time being. Next, we can go from pi over 4 to pi over 2, which landed us over there. And next, well, let's actually go ahead and sketch the next point at an angle of 3 pi over 4. So that angle would be basically bisecting quadrant 2 for us, except what do we notice? Our R value in this case is 1 minus the square root of 2, which is approximately, minus 0.4 and change. So rather than moving out in the direction of the positive direction along the angle of 3 pi over 4, we reflect over the origin to land that point. So we're somewhere down there. So let's just go ahead and connect those 2 points. Again, pi over 4 to 3 pi over 4. It looks like we're doing something like that. And then we can connect 3 pi over 4 to pi. And we could keep doing this process at an angle of 5 pi over 4. Let's see where we normally would be. 5 pi over 4 would normally be somewhere in quadrant 3, except we're going to see the same thing happen where our R value is also going to be negative, and it's also going to be roughly minus 0.4 and change. So instead of being out this direction of 5 pi over 4, we reflect over the origin again, a distance about 0.4 away. And we can connect those points, pi to 5 pi over 4, like so. All right, next we can go from pi over 5 over 4 to 3 pi over 2. So it looks like we're again starting at this point, ending at that point along the negative y-axis. We just connect them with the straight line. Again, we're just trying to sketch what this curve sort of looks like. And then what do we have next? Oh, we have what happens at 7 pi. Ooh, that should not be a 2. That should be 7 pi over 4. And at this angle of 7 pi over 4, our R value is 1 plus square root of 2. So we'd be normally going along this direction in the quadrant 4. And we're out a distance of 1 plus square root of 2, which is 2.4 and a lot of change. So again, we're moving out this direction about 2.4 and then ending there. Okay. So connecting 3 pi over 4 to 7 pi over 4. Just draw a straight line. And then finally connecting 7 pi over 4 to where we began at 2 pi, just lands us there. So this is a really crude sketch of sort of what this polar curve looks like. Again, we've used straight lines just because we only have a couple points that we're really connecting through. If we wanted to make a smoother or more curvy kind of sketch, we could have added more points in between or more angles between, say, 0, pi over 4, pi over 4, pi over 2, and so on. So that's method 1, though, basically asking us to make a table of points and then plot those points out and connect them. Method 2 is a lot different. This is where we're actually going to use a sketch in the R theta plane and use that sketch to help us sketch the polar curve where it lives in the XY plane. So just so we're all on the same page right from the get-go, this curve that I have right here is the curve of R plus, or R equals 1 plus 2 cosine theta, except this is in the R theta plane. So this is not the polar curve representation in the XY plane. This is the R theta plane. And why this is going to be useful is we're going to use the same idea that we use for parametric curves and basically ask ourselves, what is happening to R between certain values of theta? Or for us for parametric curve, this was us asking what's happening to X and Y between specific chunks of that parameter, which a lot of times we call T. So I'm going to just make a little XY plane for us to start sketching on. And we are again sketching that same polar curve, 1 plus 2 cosine theta. So let's think about how we can use this information in the R theta plane. And some of the aspects that are useful for us is the first thing we do is sort of just see what is the largest value of R, what's the smallest or minimal value of R. It looks like for us, the largest value of R can be is 3, and the smallest value that R takes on is, well, a -1. And some other notable points for us is basically where R goes from positive to negative, or where R equals 0. So it looks like R equals 0 at these 2 points here. And what's nice is we can actually solve for those particular angle values. So we have R is equal to 1 plus 2 cosine theta. And if we want to find what the angle value is at those 2 points, basically what theta is, we can set that equal to 0. And what we end up finding is we have that cosine of theta is equal to -1/2 at those 2 points. So those 2 points must be, well, theta equals 2 pi over 3 and 4 pi over 3. All right, so those 2 angles basically are 2 pi over 3 and 4 pi over 3. So maybe I'll just go ahead and just write those down. And one of the reasons why I like doing it this way is there's some special things we can draw conclusions about R from this plot in the R theta plane. So for example, between an angle of say 0 and this angle of 2 pi over 3, we can see what R is doing. In this entire angular region, R is going from something positive, R equals 3, and R is getting smaller and smaller until R equals 0 at that particular angle. So what this means down below is our angle between 0 and an angle of, say, 2 pi over 3, we know R is going from something positive to something equal to 0. So let me just plot this really quickly, just so we're on the same page. Basically, in this angle, the region, we are looking at the angle between 0 and 2 pi over 3. R is going from something equal to 3 at an angle of 0. So an angle of 0, R is 3 steps away from the origin. And then at that particular angle of 2 pi over 3, which would be somewhere in that quadrant 2, R is equal to 0. So why this is important for us, oops, I actually want to keep that angle there, is well, as R is changing, it's going smaller and smaller. So we know our curve, as we're nearing that angle of 2 pi over 3, we eventually need to circle in to R equals 0 at that very specific angle. So that's very helpful because it helped us automatically basically sketch a lot of points right away in the XY plane for our polar curve. So just make this a little more color coordinated. All right, so that was our first kind of sketch there. What is happening between angles of 0 and 2 pi over 3? And we can do a similar thing actually for angles in that last bit between 4 pi over 3 all the way to 2 pi. So 4 pi over 3 for us, that angle would be Again, the angle starting off at the x-axis, going to that point in quadrant 3. So what we're looking at now is basically what is happening in this region for our polar curve. And well, what's happening is at an angle of 4 pi over 3, r is equal to 0, and then r is equal to 3 again. So r is going from something 0 to its max value of 3 at the angle of 2 pi. So we're kind of doing the opposite case here. When we're really near that angle of 4 pi over 3, r is equal to 0, but then as we keep going around, or that angle is going from 4 pi over 3 and going closer to 2 pi, r is getting larger and larger. And the max value it reaches is a value of r equals 3. So that's what's happening between those two end regions. And the third case we need to consider is, well, what happens in this sort of middle region here between angles of 2 pi over 3 and 4 pi over 3. So that's asking what is happening sort of in this region. And well, what do we see about our function in this region? Our function is negative, or r is negative in this particular region. So what that means is whatever sketch we get over here, we would actually reflect over the origin. Now that wasn't actually a sketch, that was just to say, whatever we're doing, we're reflecting that over the origin. So let's take a look at what's happening in that particular region. Well, we know r is equal to 0 at those two angle endpoints. And then sort of halfway through, we have r is equal to -1. So what that looks like is, as we're sweeping through these angles, going from an angle of 2 pi over 3 to an angle of 4 pi over 3, r is increasing in absolute value. It's just, since it's negative, we reflect that over the x-axis. So if this thing wasn't negative, and I'm going to draw this in gray, we'd have this kind of shape. And what that means is, well, close to 2 pi over 3, r is 0, but as we get closer to pi, r gets larger and then it gets smaller again. So we're actually doing something like that between those angles. But since r is negative, that's not actually the sketch of what's happening between those angles. Instead, that entire thing gets reflected over the origin. So what's actually happening is, over the origin, we get this loop. And I'm going to get rid of that gray loop because that's not actually part of our polar curve. That would have been part of our polar curve if r was positive, but since it's not, we reflected that over the origin. So this is actually what this function or this polar curve looks like. Just by using the curve in the r theta plane to help guide us and ask the questions of what's happening to r between specific angular regions. R is going from something positive, like in this first case, r equals 3. And then as we get closer to an angle of 2 pi over 3, r is equal to 0. So r is decreasing in that entire interval. In the opposite sense, near 4 pi over 3, r is 0. But then as theta increases to 2 pi, r is growing back to a value of r equals 3. So near that angle of 4 pi over 3, r is 0. But as we keep sweeping towards 2 pi, r just keeps increasing towards 3. And then in this middle region, between the angles of 2 pi over 3 and 4 pi over 3, r is always negative. So we reflected that entire little loop over the origin, and that's how that ended up in quadrants 1 and 4. But what we see is near 2 pi over 3, r is equal to 0. And near 4 pi over 3, r is equal to 0. And then throughout this, r increases in magnitude to a distance of 1 away from the origin. Again, in absolute value, r increases. But since r overall is negative, we reflected that loop over the origin. So that's the two ways in which we can plot polar curves. The thing I want to emphasize for plotting polar curves is we do this in a rather kind of slow pace. It's not clear what a polar curve should look like, usually right from the get-go. So we either have to plot a few points to get a sense of the curve, or do kind of this method too of sketching the curve in the r theta plane, and then actually looking at the polar curve representation in the xy plane.